Good morning. So we will start
Hi,
to
doctor.
do problems on chapter 15. A 30 millimeter thick plate made of low carbon steel is to be reduced to 25 millimeter in one pass in a rolling operation. As the thickness is reduced, the plate width will increase by 4%. Yield strength of steel is 174 megapascal and tensile strength is 290 megapascal. The entrance speed of the plate is 77 meter per minute. The roll radius is 300 millimeter and the rotational speed is 45 revolution per minute. Determine the minimum required coefficient of friction that would make this rolling operation possible and the exit velocity of the plate and the forward slip. So here, first, let us start to see what they want us to calculate. So first, we need to find the required coefficient of friction that would make the rolling operation possible. Okay, we know that we have a formula saying that the draft, okay, so D is equal to mu square times R. Okay, so here we know that we are reducing the plate from 30 millimeter to 25 millimeter. So the draft is 30 minus 25 equals to mu square, which is unknown, times the radius. Pay attention for units. Mu is without unit, and D and R should be provided in the same unit. So if they gave us, for example, D in millimeter and radius in meter, we should convert both to same unit. So here it's times 300, and from this equation, the only unknown is mu, so I can get the value of mu, which is the minimum required coefficient to make this rolling operation possible. Now, in case mu was lower, you cannot do it in one pass. You should do several passes in order to accomplish your rolling operation. Okay? Now, this is the first question. Then they are asking for the exit velocity of the plate. Whenever we have a velocity unknown, think about the conservation of volumetric flow rate. So we have seen together last time in the course material that when we have a rolling operation, we have conservation of volumetric flow rate. So we can write that V at entrance times the width at entrance times the thickness at entrance is equal to V final times omega final times T final. Let us see here what are the information provided. First, concerning the thickness, initial and final, we know them. So we have, this is T0, it's 30 millimeter. We want to reduce it to 25 millimeters. So this is T final. They gave us an information that when the thickness is reduced, the width is increased by 4%. This sentence will give us a relation between omega 0 and omega final. Okay, so from this sentence, we can write the relation that omega final is 1 plus 4%, and 0.04 times omega initial, omega 0. So we can say that omega final is 1.04 omega initial. Okay? And concerning the speed, we know that the entrance speed is 77 meter per minute. So if you want to keep the same unit, meter per minute, then the exit velocity will be also in a meter per minute. Okay? So now we can replace in our equation. Okay, so let us say I will replace V0 by 77, and then the final obtained will be in meter per minute. Omega 0 I will replace it by 1 point, I will keep it omega 0, and for omega final, I will replace it by 1.04 omega 0, so it will be simplified. T0 is 30, so here it's times 30 times omega 0 equals to, from the other side, to V final, which is unknown, and I want to find, times omega final is 1.04 omega 0 times the final thickness, which is 25. Now I simplify from both sides omega 0. The only unknown will be V final. I can get it, and the unit of it will be in meter per minute. Okay. So this is for question B. And finally, I want to calculate the forward slip. So the forward slip definition is equal to V final minus, who remembers, what is the definition of forward slip? So look, we will see together the equations again. Okay, so here you have the summary sheet of processes equations. You can, since you can just have a formula sheet with you at the exam, but it's good to know them so you can directly apply. So I will remember, we will remember together all equations. You have all of them here. Even you have a sheet summarizing all the equations. So this is the draft, this is the reduction, this is the conservation of the volumetric conservation. You have, this is the forward slip. So it's the variation V final minus V roll over V roll. Okay. So when they ask for the forward slip, we should calculate this ratio. Already we have calculated V final now in this problem. We still need to find the linear roll slip, roll velocity. So the linear roll velocity VR is calculated by knowing the number of rotation of the roll and its radius. So going back to the problem, they gave us the radius of the roll and they gave us its rotational speed. Okay, so now we say that to calculate VR is equal to omega, which is the angular velocity of the roll, times the radius of the roll. So to find the angular velocity, we can use the rotational speed. Now just pay attention for units. If you want VR in meter per second, then omega will be in radian per second and R will be in meters. Okay, so here already the rotational speed is in revolution per minute. So to convert to radian per second, I should multiply by 2 pi and divide by 60. So I get 45 times 2 pi over 60. And for the radius, to convert to meter, it's 0.3, so times 0.3. Then you will get VR in meter per second. But if you do this for VR, you should pay attention also for VF to have the same unit. Since V final was calculated in meter per minute, to convert it to meter per second, you divide by 60. Or if you want, if you wish to keep V final in meter per minute, then here to have VR in meter per minute, you don't divide by 60 here. Okay, as simple as that. So in this case, you will get omega in radiant per minute, not in radian per second. So you can play with units as you want, just you should make sure to have suitable units. And if you work here in meter per minute, also here you should work in meter per minute. And then once you find the value of VR, you say that the forward slip is given by V final minus VR over VR, and it will give you a dimensionless number, which is the forward slip. Okay? Any question on this? So you can see here the solution. So first, in a first step, using the formula D equal mu square R, we got the value of minimum friction that we should have to accomplish the operation in one pass. Then using the conservation of volume equation, we got the value of V final, and its unit is like V inlet, it's meter per minute. And finally, to get the radial velocity of rolling, it's 2 pi rn, and the result, since we n is in revolution per minute and we didn't divide by 60, we got the result in meter per minute. And finally, we applied the formula of the forward slip. Another problem, a series of cold rolling operations are to be used to reduce the thickness of a metal plate from 50 millimeter to 20 millimeter in a reversing two high mill. The roll diameter is equal to 600 millimeter, and the coefficient of friction between rolls and work is given to be 0.50. The specification is that the draft is to be equal on each pass. So here I might need several passes to accomplish the operation, but I should have equal draft for all passes. The question is, determine the minimum number of passes needed and the draft for each pass. So first, here, in order to determine the minimum number of passes, the first step is to find the maximum draft per pass. Okay? The maximum draft per pass is given by mu squared times the radius of the rolls. So here mu is given. They said the coefficient of friction between rolls and work is equal to 0.50. So we know that the value of mu is 0.50. And concerning the radius of the rolls, they gave us that the roll diameter is 600 millimeter. So the radius is 300. So times 300. If you keep the radius in millimeter, then you will get the draft per pass in millimeter. Okay? So here, if we perform the calculation for D max per pass, we will get what is the maximum draft we can do per pass. And the total draft required, okay, D total, is equal to T0 minus T final. The initial thickness is 50. You want to reduce to 20. So 50 minus 20, you should reduce 30 millimeters. Okay? So now, to find the minimum number of passes, then you can say that the minimum number of passes is equal to total draft, D total, over the draft per pass, okay, over D maximum per pass. This will give you the minimum number of passes required. So let us see the numbers and do the analysis to know how many passes are required. So from the maximum draft, we get 6.75 millimeter. And since the total draft is 30, if you divide 30 by 6.75, you get 4.44. Of course, I will not do half of a pass. You should round this number. So you need in total 5 passes to accomplish this operation. And since now you know the number of passes, you can determine what is the draft per pass. So the draft per pass will be equal to T0 minus T final over the number of passes, which is 30 over 5. So per pass, I will have a draft of 6 millimeters. Keep in mind that the maximum draft is mu square R, but I can have a smaller draft. This is the maximum that can be achieved per pass, but I can attain, by proper arrangement, I can attain a smaller draft than this. Okay, so here the draft per pass will be 6 millimeters needed. Any question on this problem? Okay. Another problem. A low carbon steel plate is 300 millimeter wide and 25 millimeters thick. It is reduced in one pass in a two high rolling mill to a thickness of 20 millimeters. Knowing that the roll radius is 600 millimeters, the roll speed is 300 meters per minute, and the strength coefficient is 500 megapascal. and strain hardening component exponent is 0.25. Calculate the roll force, the roll torque, and the power required to perform operation. Please, when they say power required to perform the operation, you should take into consideration the two rolls. When they say just roll torque, so it's the torque per roll, okay? Now, to remember the formulas together, so here we are in this section, in the second section of equations, which allowed us to calculate the forces and the moment and power. So to do these calculations, to know the force, the average force, I need to get epsilon. Epsilon is ln T0 over Tf. So the first step is to get the true strain. Then I apply to find the average stress, I apply the relation K epsilon n over 1 plus n. And then once I have Y, I can calculate the force per roll. So the force per roll is equal to the average flow stress times the contact area. The contact area is W, the width, times L. L is calculated by approximation as radical radius of the roll times T0 minus T final. And then the torque per roll will be 0.5 FL. And the power for the two rolls will be 2 pi n FL. So now all I will do is to apply these formulas in this problem. Okay? So to start with, the first thing I need is to determine the roll force. Okay? And we have seen that the roll force F can be calculated as the average flow stress times the width times the contact length M. Okay? And I will start by calculating Y average. So this is Y average. Calculate Y average, I need to find the strain first. Okay? So here to find the strain, I will start by epsilon. So to find epsilon true in this operation, since it's a squeezing operation, so it's ln T0 over T final. Now concerning T0, I want the initial thickness is 25 and I want to reduce to 20. So T0 is 25 millimeter and T final is 20 millimeter. And always I should use same unit to simplify. And if here I use millimeter, here also I should use millimeter. Once I get epsilon, the value of Y flow average is equal to K times epsilon to the power n over n plus 1. So I need the coefficients K and n. This is why they gave me these coefficients. K is the strength coefficient, so K is 500 megapascal, and n is the strain hardening exponent. It's equal to 0.25. So I replace K and n by their values in this formula. I get the average flow stress. Now I will replace the average flow stress in the fourth equation. The width of the plate is given, it's 300 millimeters, so this is W. And to calculate the contact length L, okay, L is radical. So to get L, it's radical of roll radius R times T0 minus TF. Okay, all of these values are here. Just pay attention for units. Okay, so if YF is in, if you kept K in megapascal, then Y will be in, the average flow stress will be in megapascal. And if you multiply megapascal by millimeter square, because if W is in millimeter and L is in millimeter, you will get megapascal times millimeter square. Megapascal times millimeter square will give you which unit for F? What will be the unit for F if I have Y in megapascal and the area in millimeter square?
Gigapascal?
No, look, megapascal is 10 to the power 6 Pascal, okay? And millimeter square is 10 to the power minus 6 meters square. So when I do the product of Pascal, megapascal and millimeter square, what I will get that it is Pascal times meter square, because 10 minus 6 and 10 power 6 will simplify. And Pascal times meter square is force unit, it's a Newton, okay? Newton is Pascal times meter square. So when you replace Y in megapascal and the area in millimeter square, you get F in Newton, okay? So now, in the first step, as we said, we got the force. Now, in the second step, we need to get the roll torque. Since it's the torque per roll, okay, then the roll torque is given by T equals to 0.5 times F times L, okay? The force is already calculated. We calculated the force together. And concerning L also, it was already calculated. So just we have to replace in the formula to get the value of the torque, okay? And the unit of the torque, if F is in Newton, it depends on L. If you keep L in millimeter, then your torque will be in Newton millimeter. If you put L in meter, then your torque will be in Newton meter, okay? So always see what is the unit they asked you for to know which value to supply. Now, finally, we need the power required to perform the operation. When they say power for total operation, it's the total power. It's the power needed for two rolls. And we know that the power is given by torque. So here, since this is the torque per roll, then it's 2T times omega. And what is omega? Okay, omega, I get it from the number of revolutions. So here they gave us, or they gave us the number of revolution, or they gave us the roll speed. Because if I know the roll speed, I can deduce omega, since you know that this is VR, okay? VR is equal to the angular velocity omega times the radius, okay? So since the roll speed is given in a meter per minute, then if I use for R meter, I will obtain omega n radian per minute from this relation. And if you want to find the power in watt, you should pay attention to convert units, okay? So already to have P in watt, I should have the torque in Newton meter, and I should have omega n radian per second. So if you have already calculated the torque in Newton per millimeter, all you have to do is to multiply by 10 minus 3 to get it in Newton meter. And since omega here will be given in radian per minute, to convert it to radian per second, you should divide by 60. So you do over 60. And then when you replace in your equation, you will get your power in watts. Okay? So let us see together the details of the solution. So first, we calculated the draft as T0 minus T final. The contact length is radical of R times draft. So it will also be in millimeters, since both dimensions are in millimeter. The true strain is ln T0 over T final without unit. The average flow stress is K epsilon n over n plus 1. And since K is the unit of the average flow stress, will be the same unit as K, because the other one are without dimension. So it's in megapascal. And now if you replace your flow stress in megapascal and your contact lengths in millimeter square, then you will get your force in Newton. And to calculate the torque per roll, it's 0.5 F times L. But as you can see here, they converted the length to, by doing 10 minus 3, they converted the length from millimeter to meter. So you will get directly your torque in Newton meter. Now, after finding your torque, now you need to find the total power. So here you can use several formulas. If you want to use the formula of the coarse material, which is this one, 2 pi NFL, you should make sure that n unit, okay, in order to get P in watt, and you should provide it in radiant in revolution per second, okay? So, or instead of using this formula, you go back to the main formula, اللي هي total torque times omega. Also, you will get the same result. Here, they used to go back to this definition. So we need to get n in revolution per second. To get n in revolution per second, you have the velocity v, okay? This is the radial velocity. You should divide it by the radius to get omega, and then divide by 2 pi to get the number of revolution per unit time. So here, if you want, by doing over radius, they got omega, and then by dividing by 2p, they got n, okay? So the number of revolution per minute is v over 2 pi r. So, and after this, to get the final answer in revolution per second, they divided by 60. So once you get your n in revolution per second, you can apply the formula, which is 2 pi n times f times l, and replacing f in Newton and n in meter and n in radian per second, you will get your power in watt. Okay, and finally, you can convert. You get it in watt. It's you can convert in kilowatt by dividing by 10 to the power 3. So the value you get here is 206 kilowatt. Okay, so just here you should pay attention for units, because if you do calculation error in units, it will give you a wrong result. Any question about this problem?
Yes, doctor, بس can you repeat كيف جبنا الآن؟
Yes, sure. Okay, you have that the linear velocity of the rolls is equal to the angular velocity omega times the radius of the roll. Okay, but what is omega? How you can get omega? Omega is related to n. Okay, omega is 2 pi times n. Okay, so you can say that v is 2 pi n times r. Now, in case, but just you should pay attention for units. In case your velocity here is in meter per minute, okay? If your velocity is in meter per minute, then using this formula, v equal 2 pi n r, the radius should be in meter, and n will be in a revolution per minute, because it's the same time unit here, per minute, okay? So here, if you want to find n from this formula, n is equal to the velocity vr over 2 pi r, okay? Or if you want to write it in other terms, it's omega over 2 pi, because vr over r will give you omega. Then to go to n, you divide omega by 2 pi, okay? And since the unit is per minute, then n also will be in revolution per minute. And if you want to convert it to revolution per second, you should divide from here to here by 60. Okay? Any other questions on this? Oh. Another problem. They want us to repeat the same problem but using a different radius. So here, just we will use the same formula, but with this radius. I will just tell you what is the purpose of this question. And now we will perform the same calculation. We will get the new values, okay? And to understand what is the purpose here, we did the calculation for different radius, and we will try to do the analysis. Okay, to do the analysis and understand, we will do it. We will draw the graphs. So here in this problem, what we did, we have a radial velocity. What we are changing is the radius r. Okay, we are just changing r while keeping the same value of radial velocity vr. So vr is the same, but the radius is changing. We want to see what will be the effect on the rolling force, the rolling torque, and the power. Okay, so first, by taking the different, we have considered three values of radius. We have considered a radius of 50, we have considered a radius of 300 millimeter, and we have considered a radius of 600 millimeter. And based on the three calculations, we have calculated the rolling force for each radius, and the rolling torque, and the power. We will do the analysis together doing formula. So if we go to formulas of force, okay, the force is given by what? F. The force is equal to the average flow stress times the wedge times L, the contact length. Concerning the average strength, the average flow stress here, it's not varying because we have same K, same N, and it's the same material, and we are reducing from the same T0 to same T final. And this value will not change. The width also will not. We are dealing with the same width of the plate. What will change is the contact length. You know that the formula of contact length is radical R times draft, which is T0 minus T final. So when we increase the radius, what will happen to the force? Since we increase the radius, when we increase the radius, the contact length will increase and the force will increase. Okay, this is why, as expected from the calculation here, when you increase the radius, the rolling force will increase. Okay, now if we draw also the variation of the rolling torque, okay, so here you have the two curves drawn. Also for the torque formula, T is equal to, for each roll, it's 0.5 times the force times L. Okay, so if you want, the radius will affect more the torque because already the force is increased and the length is increased, so this will affect the torque increase more. So you have the slope of variation, if you want, of the torque with the radius will be higher than the slope of variation of the force with the radius, because you have two factors that will contribute to the increase in the torque. So now, once we got the variation, we will see, as expected from the formulas, that force and torque will increase with radius. Now, what about the power? Okay, what about the power? What is the definition of power? So to get the power is torque times angular velocity omega. Okay, and the torque, if you replace in your formula, okay, the torque is 0.5 times the force, which is y average times width. Do not confuse between angular velocity and width. So if you want here, I will put I don't know, omega rotation if you want. Okay, so it's 0.5 y times the width. The width is not affected. The length is a radical of r times T0 minus Tf. And then you are multiplying again. So if you want, you have L square because you have already F is y omega L. So let me put it in this way. You have F is omega y L. And you multiply again for the torque. Okay. You multiply again by L. So again times L. So it's L square times the angular velocity of rotation omega O. So here you can replace L square by what? L square is R T0 minus Tf. Okay, so if I replace L square by its value, I get that the power is 0.5 times Y times omega, which is the width, times L square is R times T0 minus Tf. While my angular velocity is calculated as the linear velocity of my roller, VR, over radius. So here, as you can see, radius will simplify from your equation because I have times r and over r. So you will get that your power will not be affected by the radius of your roll. So it's 0.5 y omega r times t0 minus tf
دكتور بلا ار
times VR بلا r times VR هحطها هون VR times VR. Okay. So here my power is independent of the radius, so it's constant. So what can I deduce? I can deduce that if I fix the velocity of the rolls, okay, the linear velocity, even if I change the radius, the power will not change. So in this case, for me, the smaller roll is better, or the highest diameter roll. What will be better for me? Look, if I use a smaller radius, I can end up with a smaller force and smaller torque. So in this way, with the same power, I will not have high constraint on my rolls. So if I can, this is why I have an advantage of reducing the roll radius if I use the same linear velocity, because I will need a lower force and lower torque to perform the same operation because I'm providing the same power. Okay. So from here, I can deduce that power. Okay, so when using smaller rolls, okay, I can with smaller force and torque reach the same power at the end, and I will do the same work while using a smaller force and a smaller torque. So we conclude that the same power value will be obtained for different radius if I fix, of course, the the linear velocity of the rolls. In fact, power would probably increase because of a lower mechanical efficiency in cluster type rolling mill. If you remember in the course material, in cluster type rolling mill, we put several small rolls with small radius. So this is the advantage. Of course, you might have a lower mechanical efficiency because you have several rolls, but in this case, with a smaller force and torque, you can reach the same work because you have the same power. This is why we thought about the cluster type rolling mill, which consists on using small rolls supported by big rolls to avoid bending. Okay? Any question on this? Okay, so this is, if you want, for this chapter, for chapter 15, these are the problems. You can find them on Blackboard. On Friday, I will post for you the recording for chapter 15, and which is a description of the different rolling operation, forging operation, extrusion, and wire bar drawing in detail, with a list of videos as usual to make it easier for you to understand these mechanisms. Okay, so for Friday and Monday, I will give you time to cover them because they are a little bit long. So you have maybe the PowerPoint is nearly 40 minutes and the videos nearly maybe 1 hour. So you need 2 sessions to cover them. So on Monday and Friday, you will cover them and we continue problems or chapter 16 on next Wednesday. Okay? So see you
Okay,
next
doctor.
time. Bye bye.
Bye, doctor.